Cepheid Variable star as a star whose luminosity is not constant in time, but varies periodically. Yeah, the luminosity increased dramatically and very quickly, only in like 2 days, from one time the luminosity of our sun to 1.3, meaning about 30%, okay, in 2 days, and then decrease a little bit more slowly and gradually, not exactly gradually, but exponentially, and takes longer, like 4 days. This is called a Cepheid variable, okay? The intensity, the luminosity increase, decrease periodically. And the Cepheid variable star will expand and contract with its luminosity. When expanding, the luminosity increases, and when it is contracting, reducing the size, the luminosity decreases. Okay.
I have a question
The
about for these seafood stars.
mhm.
When they contract and they expand like that, does it affect like the gravity of from it towards its other planets, assume that is in the solar system? Or will the gravity remain the
So
same?
the change of gravity will be very little because those stars are very far away from other planets and other stars, very
Mm-hmm.
far. So the interaction of the outer layer on other objects in the universe are not very much.
Okay.
Cepheid variable. Okay.
Had a big problem. When they looked up into the night sky, they couldn't tell how far away most of the stars were. As a matter of fact, before 1912, we could only accurately measure distance within a few hundred light years. Nobody knew how large the Milky Way was, or if stars outside the galaxy even existed at all. All of this changed when a researcher named Henrietta Leavitt made one of the most important discoveries in the history of astronomy. Leavitt's discovery was based on a small, relatively unknown group of stars known as Cepheid variables. These stars are called variables because their brightness changes over time, and Cepheids because the first one discovered was in the constellation Cepheus. Change in brightness can occur in variable stars for all sorts of reasons, but the changes in Cepheids occur due to helium in the star's atmosphere. When the helium is heated, it becomes more opaque, making the Cepheid dimmer, and when it cools, it becomes transparent, making the Cepheid brighter. The change in brightness of the Cepheid over time can be plotted on what is known as a light curve. The amount of time it takes for a Cepheid variable to pass through one full cycle on the light curve is called the period. The periods of Cepheids have a unique trait that separates them from other variables, which is what Henrietta Leavitt discovered back in 1912. At the time, Leavitt was studying Cepheids located in the small Magellanic Cloud, a nearby dwarf galaxy. She noticed that there seemed to be a direct relationship between the period of a Cepheid and its brightness. The Cepheids with the longest periods had the highest average brightness, while those with very short periods were generally quite dim. This revelation was incredibly important to astronomy. Why? Well, for the first time, we could determine a star's true brightness. When looking at normal stars, it was impossible to tell if one that appeared bright was actually bright or just close to us. But with a Cepheid, we could find its true brightness using its period. Then we could compare its true brightness to its observed brightness to find out its distance. For example, if a Cepheid has a long period but appears very dim from Earth, then it must be very far away since a long period implies a bright star. The most important impact of Cepheid stars, however, has to do with the stars and galaxies around them. When the distance to a Cepheid is found, it can be used as a celestial distance marker, telling us information about how far away the stars around it are. Suddenly, astronomers had a way to find accurate distances to anything remotely close to a Cepheid. This expanded our range of distance measurements from a few hundred light years to a nearly limitless range. All of this new information told us all sorts of things we had never known about distant stars and galaxies. For example, in 1924, Edwin Hubble used Leavitt's period brightness correlation to measure the distance to Cepheus in what he called the Andromeda Nebula, and discovered that it was not a nebula but one of many distinct, separate galaxies. This was one of the most important discoveries in modern astronomy, proving that the Milky Way was not alone and demonstrating just how enormous our universe is. Almost everything we know about astronomy today, from the Big Bang to the existence of black holes, we know because of Cepheid variables. They are perhaps the most important type of star in the entire universe.
Okay, so it is very important the role of Cepheid star as a tool to measure the distance to
In the
other
last video, we learned that there are
groups,
classes of stars.
uh, to measure the distance to other galaxies and counter Get that? Okay. Counterstellar something. But how? How do we measure the true distance to that Cepheid or other star near that Cepheid? We'll look into that in more detail and example with later reading. Huh? The brightness of the star increases sharply, then fades off more gradually, as shown in the light curve. And of course, the relationship between the peak luminosity and period of a Cepheid star, meaning more luminous star, brighter star, will have longer period of the change of its luminosity. Okay, and dimmer star, such as 100 times compared to the luminosity of our sun, will have shorter period, like 2 days. Okay, this period of calculated from the peak brightness here to this peak brightness, the period here is 6 days.
Okay.
Okay. So for 6 days here, the luminosity of that star is about 2,000 times compared to our sun, 2,000 suns. But how do we determine the distance from our Earth to that Cepheid? The mechanism for the period variation in the luminosity of Cepheid star is the following. Okay, this is explanation why the luminosity changes, the size, the contraction and expansion of the Cepheid. As radiation rushes outwards, it ionizes helium atoms in the atmosphere of the star. The freed electrons, through collisions, heat up the star atmosphere, which increase the pressure, which forces the outer layer of the star to expand. When most of the helium is ionized, radiation now manages to leave the star, and the star cools down and begins to contract under its own weight. This makes helium nuclei recombine with electrons, and so the cycle repeats as helium can again be ionized. The star is brightest when the surface is expanding outwards at maximum speed. Okay. So try to memorize this, try to rephrase that, because sometimes they ask a theoretical question about this. Explain why the luminosity of Cepheid star changes. Okay, it's like a assignment. Cepheids occupy the strip between the main sequence and the red giant on the HR diagram. At the beginning of the 20th century, astronomer Henrietta Leavitt discovered a remarkably precise relationship here, the linear beautiful relationship. We learn linear relation like in secondary school, grade 8, grade 9, but it applies even to astronomy, cosmology. Okay, and later we learn the Hubble's law, which is also a linear relationship, and many other relationship, exponential relationship, quadratic relationship, etc. We can linearize them using linear regression, and using like we have such as the decay m equal m0 initial amount of radioactive substance multiplied with e to the power of the decay constant and time. When we do the ln of the two sides, ln of m equal to ln of, we can do the division first. Here m equal m0, ln of that m over m0 will be ln of this thing, ln of e to the power of lambda t equal to minus lambda t. So now we have this ln as a y, this t as a x, and we have a linear relationship. So the point is that many other relationships can be linearized to make it simpler to understand and do the calculation. Okay.
Okay.
And many times when doing an IA in internal assessment, I will instruct some students to do that linearization. This make okay. This relationship, linear relation, will make the longer the period, the larger the luminosity. This makes the first star standard candles a tool to measure distance to that Cepheid and the galaxy containing this standard candles and the nearby star to this Cepheid. Okay, but more specifically, how we will look into that later, with examples, with true calculation. Star known luminosity obtained by measuring their period. Luminosity. So using this relationship, if we can collect a graph of the intensity of that Cepheid, we can determine the period, such as 6 days, and use this discovered relationship. It's like an HR diagram, which is already discovered. Okay, we can determine that the luminosity of that Cepheid star, this is the average, because it varies. Relationship between the average. Okay, the average luminosity is about 2,000 times the luminosity of the sun. Okay, and using the relationship, the apparent brightness D equal the luminosity over 4 pi D squared, we can determine the distance.
Okay.
So, but the point is how to determine this apparent brightness. What is apparent brightness?
Is it just the brightness of a star?
Apparent brightness. Apparent brightness study. Hopefully that they provide the answer. Okay, here. The formula here. The apparent brightness, they use a different letter, mx instead of b, and like b, it is simpler, just b. Okay, minus 5 log of the base 100 fx over fx0. What does it mean? The observed lux density using spectral filter. Wow, that is kind of complicated, Looking for a simpler formula. Luminosity, apparent brightness. Okay, here. The apparent brightness is how bright a star appears to be. The power per meter square as measured as a distance from the star, a distance d from the star. Okay, it is called the apparent brightness because it depends on the distance from the collector, from the telescope to that star. Because the same star, but at different distances, such as from the Earth or from the Mars or from Venus, the measurement of its brightness depends on the distance. The closer distance, the greater the brightness. Okay, and therefore it is called the apparent brightness. Similar thing with the apparent weight. When we are in an elevator, accelerating up or accelerating down, our weight will feel differently. Okay.
Okay.
So apparent brightness is simply the luminosity of the star divided by 4 pi of the d square. This equation, this product, 4 pi d square, is the area of the sphere around the star, with the distance d is the distance from the star to the telescope. Okay, so that is apparent brightness. So meaning we can use a telescope, we collect the amount of energy, measure accurately how much energy we receive in 1 second. Of course, we don't need to do the measurement in 1 second. Could be in 1 minute and then divide 60 to get that energy. And knowing that energy multiplied with the area of the collector, okay, we can calculate the apparent brightness. And the luminosity is calculated by this law, the Leavitt law. Okay, Leavitt law. So we can calculate the distance to that Cepheid. Okay, distance to that Cepheid. This is the measure with the telescope. The luminosity is calculated here on the relation. Okay. So this Cepheid star is the key, a very extremely important discovery that allow us to measure distance to other galaxies, because the old method like stellar parallax is not able to measure distance further than 100 or 1,000 parsec, which is just a fraction, a tiny fraction of our galaxy alone. Okay.
Okay.
One example. Okay, this is very important. It shows us how we determine a distance from our Earth to a Cepheid. The distance to Cepheid host light curve is shown in the figure D15, which means this one. Okay, the period is 6 days. The luminosity is 2000, exactly the same with what I told, huh? 2000, 6 days, 2000. So multiplying that 2000 luminosity with the luminosity of the Earth again, if you can remember, 83.83 times 10 to 26. I think I can remember that now, and I probably can make it a password to one of my accounts.
Oh, yeah.
I made that. I use a speed of light as the password to my bank account. Okay, so I don't forget the speed of light now. 299 458. Wait, I forgot it. Automatically saved by the browser. Okay, luminosity multiplying with 2000 with this one, we find the luminosity of that star to be 7.2 times 10 to the 29 watts. And the apparent brightness is measured with a telescope, some machine on a space telescope. Okay, and use this formula in the booklet, apparent brightness. Yeah, we can calculate the distance to that star to be 2,400 light years.